I regret profoundly not being with you, but it was just impossible. So I look forward to seeing you and meeting those of you I haven't met yet in the future. Thank you to Drs. Mascaro and De Bonis for the invitation. And I've really enjoyed following these talks. It's a very exciting conference. So what my goal is in general is to try to connect our knowledge across the different scales of the brain. Of course, there's the whole brain that's made up of regions. It's interconnected by long distance fibers. That's locally connected by local fibers that communicate through synapses. And so how can we possibly unite empirical data with the knowledge across scales? How can we understand neural information in conscious versus unconscious brain states? And how can we design novel personalized therapeutics for sleep, anesthesia, and head trauma? And if you want to go more deeply into this subject with me, you can see this paper that we published a couple of years ago. Okay, so to take it as inspiration, I want to give you an analogy, right? So we know in states of matter, there are certain microscopic phenomena where there are changes in the interactions between the molecules that lead to an emergence of macroscopic behavior, for example, that leads to solids, liquids, and gases. And perhaps similarly in the brain, we have different macroscopic states that can be unconscious, conscious resting, or conscious active states, which can be characterized by these macroscopic signals, which tend to be synchronized, large amplitude signals in unconscious brain states, which include deep sleep, anesthesia, and traumatic and non-traumatic brain injury. Whereas in conscious active states, you see these small magnitude, very complex asynchronous signals by EEG and MEG. Whereas at the mesoscopic and microscopic scales, you see asynchronous up and down states, as you've been presented several times. And this can be due to various mechanisms, as Mavi and Maurizio pointed out so nicely. And so one way to look at this is that perhaps it's changes in the interactions at the microscopic scale that's leading to the emergence of these macroscopic dynamics. So similarly, if we continue with this metaphor of the states of matter, we might be able to understand better the way signals propagate differently in the different brain states. So if we imagine the awake brain state is more gas-like, more turbulent, that the information, the perturbations might propagate much faster in space and might propagate much longer in time. Whereas in a deeply unconscious state, either the kind of ice-like state, the ice will either break and melt, and of course the brain would become conscious again. Otherwise, it will just do nothing, right? So in beautiful studies coming out of Milan from Marcello Massimini's group and Mario Rasanova and others, you can see these TMS EEG experiments you've already seen many times today, where during wakefulness, if you perturb the brain, signals propagate very far in time and space, whereas in deeply unconscious states, the signals remain local, and even if they're initially quite large. So Alan nicely introduced you to the work that led up to my work in his lab. Working together closely with Lionel Kusch and Victor Yirza, we transformed these mean field ADEX networks into virtual brain models. So essentially, we use spike frequency adaptation to change from wake-like asynchronous dynamics to sleep-like slow waves just by tuning this microscopic adaptation parameter. So we connected these mean field models based on long-range tracts that are determined by diffuse magnetic resonance imaging. We used the weights and the lengths that were also based on the data. So I think the coordinators will share with you this link. It's a link to what has become a public tutorial of my work that became Showcase 3. In particular, I'd like to thank Arno and Pierre Stanislaw for their collaboration and support with this Showcase 3. And here is a video. So maybe in the interest of time, I won't show you all of it. Essentially, if you follow this link, you will see the human, macaque monkey, and the mouse models in this public 3 species repository. So if you pop the hood, you can go into the model reference, you can go into the parameters, you can look at all the different parameters, not just the spike frequency adaptation. If you look at the data, you can open, this is the human data. So you'll see the connectivity, the basic anatomy that makes up the model. You can look at the model itself in the sources. And so now we go into the Jupyter notebooks that should be relatively well commented and easy to use. So here you import some dependencies. You plot one region on the cortical surface. For example, if you want to stimulate, as in the classical studies from Milan, the right premotor cortex, you can plot and just make sure you're in the right anatomical region. You can list all the different regions of the model. Here there are 76. Here the B values represent the spike frequency adaptation. So we've got 0 and 60, which give you asynchronous irregular dynamics and slow waves. So you can choose the stimulated region, how strongly to stimulate it. You can run the simulation, but of course, if you want to use the same parameters, you don't have to run it again. And then you plot the simulated time series. So here we've got asynchronous and synchronous dynamics. So then you can make a movie of each of the brain states. You can define the power spectral densities, which is really nice here because from the asynchronous condition, we have a peak around the alpha band, whereas in the synchronous condition, there's a peak around the delta, classically associated with unconsciousness. And in the correlation matrices that you just saw, that's the functional connectivity, where the functional connectivity becomes much, much stronger in the unconscious brain state. So here's the macaque monkey. It's basically the same. So I won't go all the way through it in the interest of your dinner. All right, so finally, these were all quantifications of the spontaneous activity in our TVB ADX model. So we wanted to stimulate the model and see if that behaves in a wake-like or sleep-like way as well. And you can see here in the low spike frequency adaptation condition, you have these small asynchronous signals. There's an effect when you stimulate. Here you can see the synchronous condition. You see a large effect, but it doesn't propagate very far in time. You can see this in space as well, plotted on the surface of the brain. And you can see here also the quantification of the perturbational complexity index, which is very high when the spike frequency adaptation is low and becomes much lower when the spike frequency adaptation is high. So I'd also like to thank Thierry Nuis for helping us with the code of this. As Mario pointed out, there are quite a few subtleties. So there was a really wonderful question earlier on about why do perturbations propagate differently in the two states? And Alain gave a really nice answer, and I'd like to perhaps continue on this discussion later. And to propose that there may actually be a kind of coupling paradox that we can understand in terms of if the networks are very highly coupled, a perturbation to one node of the network wouldn't be able to propagate. So if you're measuring the coupling in terms of the transmission of the perturbation, or in terms of the coupling, in terms of the communication, you would say that the network is less coupled, when in fact, like in the sense of the strength of coupling, it's much stronger. So the next thing I want to show you is, of course, this TVB ADX model has very many parameters. And so we partnered with Sandra Diaz and Michiel van der Vlaag in the Jülich Supercomputing Center to do a large-scale HPC grid search of 5 of the parameters that we would have liked to understand better. And so after we extracted several features to be able to see how the dynamics were behaving, And this effort was led by David and Kevin in the lab of Alain. And so David, who I co-supervise with Alain, has started analyzing in depth these results. So here what you can see is the strength of the coupling between the mean field models related to the spike frequency adaptation and the time scale of the model. So what you can see is the mean firing rate is higher, the standard deviation is lower, and the duration of the upstates is longer, meaning that these are going to be related to the AI states. So we've begun to explore whether there are other ways besides the spike frequency adaptation that the model will become unconscious-like, right? Which we would imagine is the case in anesthesia and in head trauma. It's not only due to changes in spike frequency adaptation. So here I'm showing you the results of the leak reversal potential. And what you can see actually is there are regions of the model where you can also see a transition between the AI state to the slow wave dynamics just based on changing this leak reversal potential, which is not specific, but it's a general mechanism that many of the anesthetic agents will converge upon. So if we look at this more closely, just by decreasing the reversal potential, even if the spike frequency adaptation is relatively low, which normally would give asynchronous dynamics, because the cells are all hyperpolarized, you get these slow wave dynamics, you get a shift in the power spectrum toward the delta range, you get an increase in the functional connectivity, the synchronization between the brain regions, and you get an emergence of these slow waves across the cortical surface. So finally, working with a really talented engineer in the lab, Kevin Encourt, we've increased the resolution of this model to approach more finally the resolution of cortical columns. So here we have 15,000 vertices, and yeah, you start to be able to see smaller phenomena, you know, at the scale of individual brain regions. So we succeeded to release multi-scale models of the three species, the human, macaque, and mouse brain, that display conscious and unconscious like brain dynamics in e-brains. These are all available. You should be able to follow the link. If you're not able to access them, you can email me and I can try to help you, or of course the e-brains administrators. And these seem to mimic mechanisms of sleep and anesthesia. So in the future, these models we hope will be useful for understanding traumatic and non-traumatic head injury, for developing personalized models for neurology tools, to predict novel therapeutics, to study mesoscale phenomena involved in coding different brain states across the whole brain. So I would like to thank all of you, first of all, and your patience, and all of my very, very talented collaborators and Alain Destex for having supervised this work.